Welcome to homework.
So here in this problem we are given that 2 kg of saturated water vapor is at 600 kilopascal and is contained in piston cylinder device. So the initial condition P1, it is given as 600 kilopascal, and you can see this thing on a TS diagram also, and the state 1 is saturated water vapor, that is why it lies on the saturation curve. Now the water expand adiabatically until the pressure reaches 100 kilopascal. So P2 is given as 100 kilopascal, and we are given that work produced by the system is 700 kilojoule. So this is 700 kilojoule, and there are two parts in the equation. In the A part we have to calculate the entropy change of the water in kilojoule over kg Kelvin. So first of all we will be using the table A5 to get the required input data. Now the state 1 is P1, we are given as 600 kilopascal, and because it is said that it is saturated water vapor, so we can say that the dryness fraction or the quality of water will be 1. So at this state we'll be calculating the value of specific internal energy and the specific entropy. So specific internal energy from the table A5 will be 2566.8 kilojoule over kg, and the specific the specific entropy will be 6.7593 kilojoule over kg Kelvin. Now next we'll be calculating the U2 specific internal energy at point 2, this thing. So for that we'll be using the energy balance, energy in minus energy out, it is equals to change in energy of the system. So energy in we have nothing, so it is 0. Energy out we have the power output or the work output, and the change in energy means the change in internal energy here. So M times U2 minus U1. So here we will be calculating the value of U2 from this equation. So U2 will be equals to U1 plus W out divided by M. So U2 we can calculate the value of U2 from here. So U1 we know it is 2566.8 kilojoule over kg, plus the power output is 700 kilojoule divided by the mass. So mass in the equation we are given as 2 kg. So divided by 2 kg. So after solving this we'll get the value of U2 as approximately 2216.8 kilojoule over kg. So we have obtained the value of U2 as it's 2216.8 kilojoule over kg. Now again by using the table A5 we can calculate the value of S2 and S2 at this point. But before calculating the X2 we have to calculate X2, the dryness fraction at this point, and then we can calculate the value of S2. So X2 we know it will be equals to U2 minus UF divided by UFG. So first I will be calculating the value of S2, oh sorry, X2. So let me calculate here. So X2 will be U2 we know it is 2216.8 minus UF. So UF corresponding to this pressure 100 kilopascal will be 417.40 divided by UFG will be 2088.2. So after solving this we'll get the value of dryness fraction as 0.8617. Now we can calculate the value of S2, the specific entropy at state 2. So S2 will be SF plus X2 times SFG. So SF corresponding to this pressure 100 kilopascal will be 1.3028 plus X2 we have calculated as 0.8617 times SFG is 6.0562. So after solving this we'll get the value of S2 as nearly 6.5215 kilojoule over kg Kelvin. Now we can easily calculate the change in entropy. That change in entropy delta S will be equals to S2 minus S1. So S2 we have 6.5215 kilojoule over kg Kelvin minus S1 we have 6.7593 kilojoule over kg Kelvin. So after solving this, we'll get the value of entropy change as minus 0.238 kilojoule over kg Kelvin. So this is the solution for the A part. The change in entropy is this. Now next, in the B part, we have to sketch the TS diagram, and we have to tell whether this process is realistic or not. So here the process is not realistic because the reason is the entropy cannot decrease during an adiabatic process, and in this case the entropy is decreasing and it is shown with negative sign. That is why this process is not realistic. So I have done a mistake here. It should be a negative sign here. U1 minus, it should be there, and similarly minus will come here. Rest is same. So final answer delta S is minus 0.238 kilojoule over Kelvin. So I hope you got the problem. Thank you.